Hi, my name is Bob Grenier and I'm a volunteer with the Martin Fleischmann Memorial Project. So we have just set up the Cirrus 2 quadrupole mass spectrometer to have a look at the samples given to us out of VEGA experiments by one Henk Jurrien. We had a few problems with getting the heater started on the filament, but we've managed to do that now by letting it cool down. Hopefully it will keep working long enough for us to do the experiment. See you in a minute. Okay, so we are back in the room and we have this unit here. I'm just going to dial down the amplification here because it's a little bit hot. Okay, that's better. Okay, it's not clipping. Okay, so I'm going to go around and show this. Do you want to show it?
Do we need to show it before I put the probe in?
Yeah, I think so. So I'll just explain it over here.
Yeah.
So
hold it by the cap, though.
Yeah. So can you see it on the camera?
Yes, yes.
So here is run one. This was given to us by Henk Jurrien, and it's from a VEGA experiment. And Alan had the very good idea because he captured the gas over water. There is some water in there, and he gave us. Alan had this great idea to freeze it so that we don't get so much water going in for the signal. So right now we're going to punch a hole in it and switch over to sample port 4 and put the probe in there.
Yeah, I'm going to switch right now.
Okay, switch right now. We're going to puncture a hole or drill a hole?
Drill a hole.
Okay.
And now you'll have to change the screen back over.
Okay.
I don't know which icon that is, but...
Uh-huh.
Okay.
Yep. All right.
Is it still scanning? Yes.
Yes.
Okay.
So we have a procedure worked out.
And where's the jar?
The jar's around there. And we're not going to puncture a hole in it? And
Not here.
Okay.
On the bench.
Okay.
And I've tested this procedure already.
Okay, so for those that want to see, I'm going to move over here. This is where we are putting the hole in.
If you want to. So I did a test run, and I can't make a dimple with this without going all the way through.
Yeah.
But just enough so that the drill centers itself, and then I have a piece of Kapton tape to seal it immediately.
Oh, very good. There's the Kapton tape.
Put that back, please. You devil.
This is obviously precision drilling. There we go. That's our sample. Here. This is how it's arranged itself, like that. There you go. Right, we're going to go around the other side.
Right, and I've tested the drill is the correct one for the probe to fit nice and tight. Okay, are we ready now?
We are ready. See what we get. So, just mass 15, 17, 18. Oh, hold on. What did we get? Yeah, we got lots of hydrogen in there. Coming out at the top there. A couple of heavier things. Mostly hydrogen.
No. The 44 is what, CO2, huh?
Yeah.
But the 28 peak is still the highest nitrogen.
Yeah, of course, yes. I guess as the hydrogen leaks, it's going to drop down, but it's still... Basically, it was 0 and it immediately went up high.
Well, one advantage of having the jar cool is as it warms up, the trapped gas is going to expand, and it's going to keep the probe suction from drawing outside air in.
So on the chart, we can really see the change there.
That's hydrogen.
That's, hold on.
It says mass 4.
Is it? No, pink.
Oh,
Mass
right.
44, CO2. So there's a massive amount of CO2 coming out.
Right.
And then hydrogen shot up. What went down? Grey. Oxygen went down. So there's much less oxygen in there.
Nitrogen dropped a
Nitrogen
bit.
dropped a little bit, yeah. So the big wins. What's this purple one here? So what's this one here? Is that
Mass 15 hydrocarbons. Hard to tell. These two are so close.
yeah, yeah. Yeah. Oh, what's this one? This went up as well. This line. Is that hydrocarbon there? That's 15. Blue. Carbon 12. So carbon went up. Mass 12. 12 there. So that appeared from nowhere. There was no carbon in the air. No, not worth talking about.
No.
And then OH almost did not change, which kind of may suggest that the hydrogen is hydrogen gas in there. Because if the OH didn't change, it's not to do with the water. I would expect this to creep up as it kind of.
And where's 18? Yep, H2O.
Yeah.
Boop.
That is water, and that is that has barely changed though. It's creeped up a little bit, but barely changed.
Yeah.
Interestingly, argon, mass 40, dropped.
Well, all the atmospheric constituents dropped about that much.
Yeah, oxygen dropped a lot, but then it's got a much higher partial pressure, hasn't it?
Yeah.
Nitrogen dropped. Yeah, so the very big burst was carbon dioxide. And secondly, hydrogen without the drop in OH, without the increase in OH. And then this blue line is carbon 12, and this brown line is a hydrocarbon. So my question would be, was he running this with propane in there?
Could be.
Because we've got hydrocarbon and so forth coming in there.
Yeah.
So what is propane? That's 2CH. I'm going to get this wrong, aren't I? 6.
Right, but it would be taken apart.
Yeah, so I'm just wondering why we don't
ionization.
have the... What is the combination of that? CO2 alone is 44. Pretty steady, actually, isn't it?
Yeah, oxygen's coming up.
Yeah. And that might be creeping in, or it might be because the water's getting dissociated.
Yes.
I have to say, you've got quite a tight fit there.
I picked the right drill bit.
Yeah.
You know, I measured the tubing size, and I picked a drill that was 1/1000th less, because drills will spread a little bit.
So to give you an example, this, we could have used really expensive D-wires and desiccated the gas, but I think in the combination of Henk's rather ingenious use of jam jars, it's clearly been able to store that hydrogen within that seal. Yeah. He's been able to capture the hydrocarbons in the CO2. Obviously, the CO2 is vastly higher than the basically negligible amount in the atmosphere.
But you can see the effect of of atmospheric penetration there.
Yeah,
that-
yeah, it's creeping up the oxygen.
Yeah.
Yeah, it's creeping up.
So a short test is about all we can.
Yeah,
really
but
depend on.
it also might be the oxygen is coming from ionization of the water as it's starting to melt.
Yeah.
But the combination of what Henk's done and what Alan's done with the suggestion to freeze it, and this method is a practical and affordable way, assuming you have a Series 2 mass spectrometer.
I mean, we could be keeping the jars in an ice bath.
We could be, yes.
We don't need to, though.
No, I think this actually gives us an indication of
All right,
things.
so let's pull that out, get back to baseline, and get the next jar going.
Okay, let's do that. So that was that part of the test.
You're going to archive this?
I think we'll put a waypoint in here so we can put a note. Where is it? Where is the actual? Now I've got to remember how to view the whole thing.
Yeah, it's not the friendliest interface.
Yeah, but there's a way to. Where is it? View. Where's the viewing on this? It's somewhere here. Trim window. Okay, X-axis scroller. No, that wasn't it. That was it. And it's not scrolling the X-axis. Not very helpful. We can make it bigger. I thought the X-axis scroller was meant to actually scroll the X-axis. One would have thought so, but it's not. No, not helpful. This is where memory's a wonderful thing.
Yeah.
If I had some. I'm pretty certain I could scroll that in the past, and I can't right now. We're using the X-axis scroller. And it's not allowing me to do it, which is highly tedious. Oh, this is what I remember. You had to rewind it like this. You can scroll display. Okay. Okay. I don't want to break that right now.
Yeah.
I've got it on the recording, so I'm going to do a note here, which is somewhere. There's like something that looks like a note. Is it that one? Historic live data. Okay. Oh, there we go. Can I go back here? There we go. I can go back. There we go. Finally. It should update in a second when it gets to the end of here. Yeah, so that's what I did before. So we can go back here, and this was is that a note?
Sample 1.
No, one of these is a note. I'm going to get there. This is when you are. Oh, this one here. I want to go something like that. Let me go. Note. Is that 8:17? That isn't 8:17. No, that's now. I want there, which is what time? Does it tell me? No. That's 28 minutes, roughly. Well, it's not helpful at all, is it? This is, I don't want elapsed time. Anyway, this here is sample 1, if you're listening, where I've got it here. There you go. That's sample 1, and we're going to go over here. We're going to swap in sample 2, and we'll leave it at that, because my memory's failing me. Okay, I'll go and get sample 2, if you'd like to do the honours and take that one out. Thank you, Alan. Be here with you in a second. Oh, so speedy.
Practice. Engage, Captain.
Engaged. Wow. Okay, this is run 2, and we have a big change. Okay, so we saw the big drop from the mass carbon dioxide went down to, well, it went down 2 orders of magnitude back to atmospheric down here, and it shot up. This one has lower carbon dioxide. Again, the oxygen here, or nitrogen rather, has dropped down a bit. And again, the hydrogen is up. So it's fairly consistent. We've got the CO2 there going up. Quite similar, actually, to before. Ah, there's the true time.
These two drop out completely.
Yeah, completely. That's the hydrogen completely goes.
Yeah.
Which is good. I'm glad there's not much hydrogen in your lab, Alan, because that would be dangerous.
I can change that if you want.
No. I'm happy with the way it is.
Yeah.
Yeah, so. So now I've got this on actual time. I can actually put in a reference here. Annotate at selected time. Let's do that. There we go. It's a bit easier, isn't it? Sample 1.
Start.
Henk VEGA. Okay, so that is sample 1. You can see if I click on that, it tells us what it is. Or I roll over it. Or I click on it. There we go. You have to move to the right place.
Yeah.
Okay, so then we'll go over here. I will go back to here. This is the atmospheric settling. So this is the settling process here. Settling to atmospheric over here. And we go along here. And over here is where we took out sample 1, which is at that point. And this is where we added sample 2. Okay. So again, similar sort of pattern. The mass argon 40 drops. Mass 44 CO2 rises, not to the same level as it was over here.
Pretty close.
Pretty close. Yeah. The oxygen drops. Hydrogen comes up. We've actually got more. What's the blue line again? The carbon 12. There's actually more carbon 12 here in this one. So. This is a practical way to do gas testing. Even traveling over international borders, carrying a gas, a small vial containing extremely small quantities of protium. Extremely small quantities, but mostly CO2.
Yeah.
It would appear. Carbon dioxide.
And this was gas evolved from inside the VEGA cell?
Yeah, so what he found was once you get it running, it started to produce gas. And so he wanted to find out what the gas was that it was producing. Now, I do know for a fact that in experiments he puts firstly, it's a non-baked out large volume cell. So if it warms up, it'll start to degas from all of the surfaces.
Is it derived from a propane bottle?
Yeah. So,
well, there you go.
So you've got these massive surfaces which will have been exposed to, even from the beginning, hydrocarbon gases.
Yeah.
Depending on whether it's a pure propane or a mix, because some of them are butane and propane, methane, whatever, but normally propane and butane. And then I know in some of his experiments he physically adds hydrogen, and he also physically adds not the cleanest metals in the world, and typically all metals will have carbon on them.
Right.
So the idea that you're seeing in this particular instance carbon dioxide, carbon and hydrogen is not unsurprising.
Yeah.
There's a little blip down here of something yellow, which is heavy 17O water, potentially. You can see the little blips down here. It is this 19, mass 19, which could also be fluorine unreacted.
This is right at the noise floor of the detector, and if you change the sensitivity to 5, you'll see all kinds of blips like that. So it wouldn't surprise me if it was just noise.
But do we get the noise when we have it turned off? Go back. Not a lot of noise down here.
True.
But that's a different sample. There's definitely no observation up to inserting the first gas. And then we start to see it here in this first sample. And then it goes back to 0. And then in the second sample, we've got a lot more of it.
Okay.
Whatever it is. Now, is that 19 achieved through heavy 17, or is it through DDs?
He doesn't have deuterium in his lab, does he?
No, but normal water. Where is it?
It's a tenth of 1%. It's
is 18, isn't it?
Yeah.
So, has he synthesized heavy 17O water or DHO in larger quantities?
Or traces of fluorine.
Which I think is highly unlikely. The idea that fluorine would be, unreacted, and when fluorine reacts with anything, thank you. No, but it's not there in the original.
Could be baking out. I'm just saying, it was in there today.
Yeah. So Alan's just pointed out that in the sample pipe there might be residual amounts of fluorine because he chose to use a a control test material, which was a fluorocarbon, a free spray.
Yeah.
Let's just see.
And that showed up when I did the test as mass 50.
Tetrafluoroethylene.
But it would break down in the ionization path.
Yeah.
To what's it called? Difluorocarbene.
Well, my point
50.
still rests is that when
right, but there's nothing at mass 50, so it isn't residual from my test.
No, and also it would be a pretty useless process gas mass spectrometer if anything you put in it stayed in there for the rest of the process for the rest of the days you used the device.
True.
I mean, it would be utterly pointless.
Yeah. Yep. All right. Sample number 3.
Sample
please.
number 3. Okay. So I guess you can do the taking out as you wish. I'll go and get the other one.
Door number 3.
Door number 3. before I hand this over to the maestro of hole making, I just want to show you the lovely amount.
Yeah, don't warm it up,
I'm
please.
not warming it up too much, Alan.
Yeah, all right.
I just wanted to show the large lump of ice that's at the bottom here.
Yeah.
There's a large chunk of ice, which Alan's wonderful idea prevents us from sucking in because it's frozen. Okay. Yeah, lovely. What do we see? Oh, boom, straight up. You just start seeing these come up here. That was basically not there, and it was just nice to watch it come up.
Yeah.
Actually, that'll all be on the recording. Okay, so this was sample 2 out, so we will put a note in there. Okay. And then this was, oh, hello. This has got a fairly stiff. I wonder if these are samples taken sequentially over a long run. It would make sense, unless he was trying to fool us.
That's more of the Mass 19.
That's more of the Mass 19, yeah.
All right.
Straight away.
Yep. And what's at 39? That's another one that's about that level.
Well,
could be argon, isotope of argon.
Well, you can add things in. You can add a line. Anyway.
Yeah, there's all kinds of trace combinations that come from the ionization.
But as a methodology, I think, Alan, it works.
Yeah.
It works. It's assuming you have a gas mass spectrometer for at least a really good idea of what's going on without spending thousands on expensive D-wells, it works.
Right. Now, he extracted this through a bubbler.
Yeah.
And what was in the bubbler? Was it DI water? Or was it tap water?
I think it probably was tap water, but like calcium doesn't tend to vaporize very easily.
No, that's true.
Tap water tends to have a partial pressure very similar to atmospheric pressure of gases in there.
Yeah. So, I mean, in the lab, you would have the bubbler output go through a freeze trap.
Of course, yeah. And then you would have a nice dry gas. Or rather, the output from the bubbler.
Yeah. But it looks pretty much the same as the other two samples.
It does.
Except
carbon
for
dioxide's a little bit lower again. So this one was lower than that one.
Yeah.
And that one was lower than that one. Okay. So what is the hydrogen trend? The hydrogen trend is this black line that shoots up here. So that one was lower than that one. And this one is higher. More hydrogen in this one. But this has got a definite signal here now. Whatever that is, that 19.
Yeah.
So if this is sequential, there was nothing in the atmospheric. Then we turned it on and we started to get a bit of a signal here. A little bit of a signal. Then it went back down to 0 with atmospheric. Then it was a little bit more in the second run and then back down to 0 in atmospheric. And then here we've actually got a fairly, well, it's a low signal, but is that...
It's above noise.
Yeah, is that HDO or is it H217O? My gut feeling, if it's supporting the claims of Benjamin Huang, it's going to be 17O. And that is also supported by seeing a D signal in here.
Yeah.
We've just seen this little spike of a D signal for the first time.
All right.
I mean, it's only a little blip, and maybe we won't see it again, but we just saw it.
Mm-hmm.
Of course, D does exist in normal water.
Normally, you wouldn't see it in
No.
a trace like this.
And it was only the one blip we just saw there.
Yeah.
Now, are we seeing anything at 17? We are, aren't we? 17. Right. So, is the 17 signal? What is that? Oh, that does that go up? Is that line? I think it is. No. What is it? 17 is OH. It's the green. It's pretty flat. Is it?
Yeah.
Oh no, I don't know. Okay.
And that's normally seen in atmospheric sampling.
Yeah.
You know, water vapor gets
No,
ionized.
that's not my point. The question is it actually OH or is it 17O?
Dry trap.
Yeah. Because it's in that second sample, it's definitely going up here.
Yeah.
And it's still high here.
Yeah.
We'll watch that when we close. Oh, hold on. I think we've just lost our filament. Well, that was nice whilst it lasted. I think we got the data we needed, but our filament has decided it's not going to work for us anymore.
Yeah.
I will try and switch the other filament on. See if we can get some joy out of that.
Nope.
No, it's obviously decided it's not going to let us play anymore.
All right.
Anyway, we got the data we wanted. Thank you very much, Alan. Well done. That was that. It's lucky it's a quick experiment.
I'm tending to think that the broader range on the quadrupole, the machine gives the filament extra current, and then it overheats or the current gets too high.
Okay.
Because I haven't seen this in the past on anything at mass 50 limit.
Okay.
So.
All right. Well, that is that. Thank you, Henk Jurrien, for your supplication or supplying these supplying these samples to us. And thank you again to Alan for the use of his equipment.
Well, and thanks to Fran Tanzella and the folks at Berluen to donating this equipment for our use.
Really, it's a very, very important tool, as you can see. So thank you very much for your time. I'll see you on the next video.